Beleza, acredito que a gente está online, né? Ok, boa noite, pessoal. Eu sou o Josias. Hoje eu venho aqui em nome da APG para trazer para vocês mais uma live do nosso capítulo. E hoje a gente vai trazer um pouquinho de modelagem química com o Douglas Waples, que está aqui com a gente, diretamente de Cairo. O Douglas é CEO da Sirius, idealizador do software Novva. É um software de modelagem geoquímica, especial geoquímica orgânica, foi crucial na nossa participação no IBA de 2021, na nossa campanha aí que nos levou a ser campeões da competição. Inclusive, o nosso primeiro episódio é do podcast Sedimentae, no qual a gente conta um pouco da nossa experiência, já está disponível, tanto Spotify e Deezer. Agradeço a produção, se deixar aí no YouTube o link, e lá a gente conta com detalhe como é que foi essa jornada. Mas voltando aqui ao nosso apresentador de hoje, o Douglas Waples, ele é formado em Geologia pela Colorado School of Mines. Deixa eu pegar a cola aqui no LinkedIn rapidinho. Douglas fez o PhD na Universidade de Stanford e trabalhou por 4 anos, entre 73 e 76, na Chevron. Também foi professor associado na Colorado School of Mines, trabalhou como geoquímico na Mobil e há 30 anos ele trabalha como consultor livre, né? E há cerca de 9 como presidente da própria Sirius. So, Douglas, I pass the word for you. Thank you again for being here, directly from Cairo, Egypt, to talk to us a little about geological modeling. Be free and thank you again.
Boa tarde. Obrigado, Josias. E parabéns por ganhar a competição de IBA.
Muito obrigado.
Infelizmente, não falo mais que pouquinho de português.
Fala muito bem.
So we're going to have this lecture. In English. Thank you for listening to me in not your native language.
That's okay.
You probably don't know exactly why you're here, and you probably know it may have something to do with basin modeling, and it does, but it doesn't go in the direction maybe you were expecting. Basin modeling is an old term. Today it's more commonly called petroleum systems modeling, but they're fundamentally the same thing. Historically, there have been 1D basin modeling, 2D, 3D, and actually all of these have an extra dimension, which is time. We don't mention that when we're talking about the number of Ds, but it's very, very important to recognize the power and importance of time in all of our discussions. Traditionally, basin modeling and petroleum systems modeling have had two different versions or two different focuses. There's been a 1D focus, which was on the question of maturity, which could include vitrinite reflectance, hydrocarbon generation, cracking, and expulsion. Whereas the 2D and 3D modeling added in, on top of the maturity questions, pressure and hydrocarbon flow, enabling it to model hydrocarbon migration, trapping, preservation, and so on. These two different applications have overlapped. They work together sometimes, and other times you'll emphasize one or the other. Today, we're not going to talk about 2D or 3D or pressure or hydrocarbon migration at all. So we can just forget about that for the moment. We're going to be looking at 1D modeling. In fact, we're going to remove all the questions related typically to 1D modeling, which are focusing on maturity. Instead, we're going to do something quite different. Something that's really new. The new perspective, which is being promoted by me and I seem to be one of the few, or perhaps the only one, is to use 1D modeling not only or instead of for maturity calculations to learn about geologic history. This is an application which may have been in the background for some people during the early days or previous times in basin modeling, but it has never been a focus of any kind of basin modeling. The focus instead has been on numerical answers. How mature is my source rock? How many billion or million barrels of oil and what GOR do I have in my prospect? Questions like that, very bottom line oriented questions that would be of importance for exploration programs, but they don't really advance scientific knowledge. So what I'm going to do tonight is introduce you to what I call the beauty, power, and utility of a technique or technology that I have developed and I have named Integrated Geohistory Analysis, or IGA. This is my own name. It's a relatively new contribution. I'll give you a little rundown in a moment on the history of this. The initials IGA, of course, stand for those three words, but the meaning is the integrated refers to integration of many different disciplines or areas of interest within the geoscience, such as biostratigraphy, tectonics on different scales, sedimentology, geothermics, even geochemistry. So we're looking at everything that's related to soft rock geoscience. Geohistory is in the name because the technology focuses on creating and interrogating or extracting information from geohistory plots. And the analysis refers to the fact that this is a very analytical technique that is used in a very scientific way to advance our understanding. I want to change my focus just for a moment here and comment that today we are living in what I would call an age of narratives. The word narrative is similar to the word story. And a narrative, like a story, can either be true or fiction. What we're aiming for is true narratives, as true as we can possibly make them. Why narratives? Well, narratives have two very important values for us. First of all, they will provide a solid logical foundation for whatever we are thinking and saying. So our narratives will be created on a logical foundation. And this is a point that is poorly understood by geoscientists, is that narratives provide an emotional framework. No, they don't necessarily make you cry, but the point is, if we want to get our message across, our narrative is a powerful way to do it because narratives or stories touch the emotions. That's why we watch so many shows on television or in the cinema, why we read books. It's because the narratives we're hearing, seeing, reading about touch us inside. And that is very important for successful communication. Therefore, narratives have both the technical part and the emotional part that will lead to successful transfer of ideas and information. Narratives are also valuable in dealing with what some people call the unknown unknowns. That is the things that you don't know, but didn't know that you don't know them. These can be very, very dangerous. And narratives are one way to discover these and deal with them. So it provides us opportunities that we wouldn't have if we weren't busy creating narratives. And my thesis that brings me to developing IGA and giving this talk tonight is that basin modeling, which has been rebranded as petroleum systems modeling, but it's really nothing more than a rebranding, has not fulfilled its potential as a generator of narratives. People haven't asked it to do that job, and it hasn't volunteered. And I believe that although they may not recognize it, the geoscience community is hungry for more narratives and better narratives that can generate exploration enthusiasm and ideas, particularly the ideas. So if you think of IGA as a generator of ideas, you will be very close to the mark. In fact, I believe that integrated geohistory analysis can become the principal generator of exploration narratives. It has all the tools to do that. And therefore, IGA can become a key technology for geoscience education, such as you are undergoing now, theoretical research as well as applied research, hydrocarbon exploration, exploration for minerals in soft rocks, and possibly even such things as engineering geology. In other words, there's something in the lecture tonight for everybody, because this is a technology that is teaching us about the rocks and their story. And then it's our responsibility to understand that story as well as possible so that we can use it for whatever purposes we need it for. The most important word in IGA is a very simple word. It's why. Because the basic idea of IGA is to bring together all these loose parts from people who may not even talk to each other. They certainly don't read each other's papers. People such as sedimentologists and plate tectonic specialists, for example. It's going to bring together their work and their expertise, and they can play important roles in the entire process. But we have to be asking questions. The question why. For example, I have a basin and I have slowly deposited carbonates, and suddenly I discover that I have rapidly depositing clastics. We ask why. Why is there a change in lithotype? Why is there a change in rate? And we research those questions by thinking, by reading, by asking questions of experts and people with knowledge of that particular area. So you should always be asking why, because if you can ask why and you can't answer it, you have work to do. You need to try to answer every why question. I want to take you through the history of IGA a little bit, although it was not called IGA for a very long time. But it's now 50 years old. This is its 50th birthday since the invention or first publication of a burial history plot by Nikolai Lopatin in the Soviet Union. 50 years ago, the roots of IGA were born. And this is what we saw. It was not like any diagram that most geologists had ever seen before because it's a time depth plot. It is not a cross section. Geologists that I talked to as early as 1975 looked at this and had no idea what it was. And yet today it's quite common. This is a plot of the burial history. As the line goes down, it represents sedimentation. As the line goes up, it represents thinning by erosion or some other process, if you can imagine one. That's all it did, but it was revolutionary. So we have roots that are 50 years long in this. The datum for a burial history plot is the solid surface. Very important to know that. And we can have in a diagram a series of lines that represent different strata in the section. All the lines are parallel to each other because in these early plots, which we were doing with pencil and graph paper and a ruler, we didn't consider compaction, so all the lines were parallel to each other. It made it simple to draw, but not scientifically quite right. So we could look at many strata at one time. And of course, through time, we have come up with computers, programs, software that will do this for you and allow you to automatically include such things as compaction with no pain and suffering. So they're not only doing it more quickly, they're doing it better, and they'll create pretty diagrams like this. And these can be very powerful. For example, you may notice in here a little blip in each of these strata. That's at 66 million years ago, and that represents the Chicxulub meteorite impact, because this model comes from the country of Belize, which was quite close to the impact center, and there is evidence in the rocks in Belize for this event. So we can even put such a small event as that into our burial history model. But this is, again, despite the high technology, it's just a burial history model with the datum at the top of the solid surface. But as we move on through time with software, and there's quite a few software programs that have been developed to do 1D modeling like this. This one, Novva, is the one that your team used in the IBA competition. It is the one that I developed and am marketing, and I am using it for my own exploration consultancy work. The diagrams you see in this talk will be generated almost entirely by Novva, and you'll have a chance to look at it yourself on our next meeting, and then even get yourself a demo copy if you would like. This is a different geohistory plot. It looks totally different for many reasons, including the time frame covered and the shape of the curves and so on. But it's not really any different in substance from the other one. So we have a burial history plot here. And our next milestone then is the first advance over Lopatten's original burial history curve, which was the invention of the geohistory plot by Professor Van Hinta in the Netherlands, just 7 years later. Now, what is a geohistory plot? Well, in a geohistory plot, the datum is no longer the top of the solid material, it is paleo sea level. And what you see is that the cyan color there is flat across the surface. So where there was seawater, we have a flat datum. back in the Triassic, in the purple area, you'll notice that the land is actually a little bit above that level. And so it's showing that the ground level was above sea level at that point. You can see instantly that there's much more valuable information in this plot than in the burial history plot, because now we can begin to think about gross depositional environment, changes in water depth. Why did the water depth change? Why is it dry land in this period and underwater in another period, and so on? So we can begin to ask questions. There are some very obvious ones here. For example, why does the ocean fill in very, very slowly here and then suddenly deepen very, very quickly? What is going on to explain this? So this is a series of why questions that are coming out of our creation and interrogation of a geohistory plot. This is the heart and core of IGA, to create these as accurately as possible and then to interrogate them as intensely as possible. And that is a skill that one develops through years of practice. The next milestone, a very small milestone, was a paper published only 4 years after Van Hinta by Peter Vail, who really had no history in geohistory analysis, discussing the great potential and bright future for geohistory. He saw it, but never pursued it himself. So out there, 40 years ago, we already had the groundwork laid for us to take full advantage of IGA, but we didn't do it. It took another 20 years for me to present my first talk that I could reasonably say was a precursor to IGA. I called it at that time the hidden benefits of 1D maturity modeling, because what I was doing was focusing on understanding what the plots were telling me and teaching me about the geological history, rather than worrying about what maturity level is my source rock. I was more interested in the unconformities and the changes in water depth and so on than I was in whether my source rock was mature or immature. So I was moving into a new realm, which says what's interesting about these geohistory plots is not just those numerical final answers that the boss wants, but the knowledge that I can get if I build good models and look at them carefully. But it took me another 10 years to actually publish this. So you can see that there's been a very large amount of wasted time in getting started on using geohistory plots. And the key for me was when I realized that with global sea level curves, such as this one, or whatever one is your favorite, we have a powerful tool that should be combined with geohistories. And so we developed something. Well, first of all, I released the Novva software in 2013, and that's on this list because it was designed specifically to facilitate IGA. And it's the only software that is designed for this purpose. Other 1D modeling software is designed for giving you maturity information, but not particularly for building and learning about the geologic history. And soon after we created Novva, we developed the eustatic geohistory plots. That's what I call them anyway. And what we see here is a beautiful example of what a eustatic geohistory plot looks like. The datum is now the present sea level. So we've changed datums here, and that means since the present sea level is 0, when sea level was high, our sea level will go up, as we see here in the Eocene, right here when we had our maximum sea level. And it was lower in the past, and it has gone down to present day. I suspect you can already see that now we have a tool which is really robust and able to allow us to analyze what's going on geologically in a lot of detail. But we still have to be aware of it, and we still have to do the work. These are only tools. What you're going to have to do is to become very sophisticated about this. And as I said before, if you're not interested in basin modeling, that's not a problem, because this type of work, geohistory modeling, IGA, needs input from specialists in all different disciplines, and some of them can become button pushers for the software, and others can become thinkers, idea generators, synthesizers, and so on for the data. So this is for everybody. It is for everybody, or pretty much everybody in your department, and anyone from outside who has come to hear this talk. I hope that you can find something in here that will speak to you. Now, why is this important? Why is the eustatic geohistory curve important? I'm going to show you in these two slides. The first is a standard geohistory plot. That's the original one, the Van Hinten type. And the red line represents tectonic subsidence. This is a location in Belize. And what we see is that today and during much of the Cenozoic, it has been above sea level, dry land. And the red tectonic subsidence curve goes up, which is the way that you get things above sea level. You lift them up. That's what most people think about. So what we are saying here is that this exposure was caused by tectonic uplift that occurred during the Paleogene, and by the start of the Miocene, it had pretty much stopped, as we see by the relatively flat curve here. So that gives us a geologic concept to work with if we are using a standard geohistory plot. But if we instead change to a eustatic sea level plot with all the same data, you see a very different story. You can see over here on the right, the cyan line is overprinted on the strata, and it shows sea level from its maximum to present day. What we notice is, again, these are indeed above sea level, but look what's happened to our tectonic subsidence line. It's now going down. There is no uplift as these rocks became exposed. Instead, they became exposed because the ocean went away. Sea level dropped, leaving them high and dry. It's a completely different understanding of this area, and it led through a rather circuitous route of thinking to developing a new exploration play by exploiting and understanding this new knowledge. So this is not academic geology. This is potentially very, very applied and practical. So, in 2020, I created the name IGA for the narrative generating technology of the eustatic sea level or geohistory plots. An important point is that IGA is everywhere. It not only operates in the realms of tectonics and sedimentation and water depth history and biostrat and so on, it operates simultaneously on different scales. So we can be talking about plate tectonics. We will use plate tectonics or global thinking as part of our background, but we can get down to regional trends, basin trends, plays, and even specific prospects. And the more levels it can operate on simultaneously, the stronger your final story will be when you put it together. Here's an example. This is the west coast of North America, Baja California, mainstream Mexico here. This is Canadian border. The Farallon plate has been subducting under that for a very long time and is responsible for two major waves of tectonics, the severe and the Laramide orogenies during the Mesozoic and into the Paleogene in some places. So if we want to understand the western half of the United States, we have to understand this on a plate tectonic scale first. And we not only have to understand it on a plate tectonic scale, we have to understand it through time as it is evolving in all these time slices from 80 million years ago to present day, so that we can properly understand the forces that are acting on these areas as a function of time. But beyond that, this is the Western United States. This is the severe fold belt, which is rather old. The Laramide provinces are out here in the lighter gray. All of these are different basins: Powder River Basin, Denver-Julesburg Basin, Wind River Basin, San Juan Basin, and so on. If you want to understand any of these basins, you need to first of all relate them to the Farallon plate subduction and all these orogenic things to the west, but you also have to relate them to each other. That means I need, if I'm working on the Powder River Basin, I want to bring in information from the Denver Basin, the Wind River Basin, and so on. So we have to put things continually in context and understand these relationships. One basin could be a good analog for another in some ways, but can be very, very different in others. And understanding your neighbors so that you can see how you're similar and how you're different is extremely valuable. We'll come back later to this diagram to make that point. But particularly if we move down to Mexico, they've got the same problem, except it's called the Cocos Plate, and it's coming from the southwest rather than the west. So if we want to understand the Pacific coast of Mexico, we have to understand first the Pacific coast of the United States, and then we have to translate that down to Mexico, rotating the plates and having a different plate motion that will help us understand how subduction of the Cocos Plate has affected the southern half of the Gulf of Mexico, the Chiapas Fold Belt, Yucatan, Belize, and so on through here. So we're continually using a telescope and a microscope to understand our systems. Let's have a look again at the Central Graben in the North Sea. Most people would say the Central Graben history began in the Jurassic, because it's well known that this is late Jurassic rifting. Here you see the LJ, you see the tectonic subsidence curve going down. This is the rifting event that created the Central Graben, rift and then followed by drift, and then some other interesting events later that we will talk about. But what I want to do right now is go backward in time and show you that sometimes the beginning is not really the beginning, because the Jurassic in the Central Graben is not sitting on crystalline basement, it's sitting on Paleozoic rocks from the Northwest European basin, which was a Paleozoic basin. So if we want to understand the rifting in the Central Graben, it's probably smart not to start in the Jurassic, but rather to go back to the Paleozoic to understand the tectonic regime that predated this, and also the nature of the rocks beneath the Jurassic that would have been part of the rifting story. And so we have to recognize that deep understanding can only occur if we look deep into the past and far to the side of our specific area of interest. So we can highlight the Jurassic failed rift here, but your analysis will not be convincing and not be complete unless you can explain what happened here and how the failed Jurassic rift is related to the earlier events. And in fact, we did have sagging and some stretching in the Northwest European basin in the late Paleozoic and early Mesozoic, long predating the late Jurassic rifting. So this can help us understand that this is actually a rejuvenation of an older extensional event in an extensional province, rather than a completely new event that came from nowhere. The idea of rejuvenation is a recurring theme that is often overlooked, and IGA can help us work with that. In particular, though, there are some other interesting things in this geohistory that I'd like to pick out. And so what I would like to do is to focus on this part of the story. Because look what happened. I mentioned it before. The ocean was shallowing very slowly. It wasn't exactly a starved basin, but this is 100 million years, and it didn't fill up. So it wasn't getting a lot of sediment. And gradually it began to fill up, and then the bottom fell out. This is a huge event, taking it down to much greater depth, and it shows up as rapid tectonic subsidence. What is this event? It surely is an extremely important one. And then what's this last little thing here? Is this real? Anytime you see something strange, you should always say, do I believe it? Is it real? But if it is real, we're going to have to explain it. What's going on here? Do we have a problem with our model, or is this a real geologic event? So one of the things I'd like to focus on, this one right here, this event in the early Cenozoic, about in the Paleocene, and see what we can learn about it. Whoops. Oh, yeah, sorry, I got to the wrong place. All right, here's a case where we found sedimentation rates and lithologies to be very, very informative. I would just say parenthetically, rates are very important for IGA. Rates of erosion, rates of sedimentation, rates of change in water depth, all kinds of rate things have the potential to be very, very informative, and they should be used as often as possible to create a story or modify a story. But before we get to the rates directly, let's look at lithologies. What we see is we're down here into the latest Cretaceous, earliest Cenozoic here, the Danian chalk, for example. Look at the lithologies here. 98% chalk. It's almost pure chalk. And then you go almost from Saturday night to Sunday morning from chalk deposited at a rate of 50 meters per million years to clastics deposited at only 10 meters per million years. There's been a huge change in lithology. This needs explaining, and it has to somehow be linked to that tectonic model, because that is exactly when this change is occurring. And one can do this quite straightforwardly. How did the chalk get deposited? Well, we had good biogenic productivity from the coccolithophorids, and we had an absolute total lack of clastic input. So we'd be looking for an environment that had no possibility of supplying clastics to this system, and its productivity, biological productivity, is moderate. It's only depositing at 50 meters per million years here. That's not very impressive for biogenic sediments. So it's not so much that we had huge amounts of coccolithophorids, we just didn't have anything else during chalk time. Then we had this transition period with very low sedimentation, no chalk. The chalk was all gone, and we have to explain that. But why is the sedimentation rate low? Because we lost all of our chalk and didn't replace it immediately. So whatever that tectonic event was, it didn't create immediately a new viable sediment source. So we're figuring this out from our geohistory plot, our tectonic subsidence curve, and our lithologies. And then what happened? Wow, we go from 4 meters per million years in Boulder time to 300 meters per million years in Horta time. 2 orders of magnitude, and we start bringing in not just clastics, but coarse clastics. So suddenly we've got a rich source of clastic sediments that we didn't have up until this point. And I'm willing to bet that this event here that made the sea bottom go down in some other location pushed something up, which became a new source terrain for these sediments. Not too far away because it's bringing in sand, but it's not bringing in sand immediately. So that new clastic source was not immediately available to this area. It took a little bit of time for it to arrive. And then after that, we see that the history has been very, very different, somewhat variable, but overall, all of these are part of a new regime that took over from the old chalk regime. So you could see we're creating a narrative out of this. And if we brought in other sources of data that helped us understand the nature of this tectonic event, for example, this event, where was it? What was the cause? It's so fast with so much quick subsidence that it makes me think it was strike-slip movement, porpoise structuring, creating a series of highs that are sediment sources and lows that are depot centers. And so we would just go through the exercise of investigating all the possible events and information that could be relevant to understanding this event. Why are we doing this? Because it's interesting, not because it will necessarily change our exploration ideas here, although it might, but knowledge is always good. And so if we understand this better than anybody else, we are going to have an advantage. Because, for example, even though it may not have any source rocks, maybe it's closely related to reservoirs and seals. And so if we understand the dynamics of this event, maybe we're going to be able to understand one important part of the exploration problem better than anyone else. And I think that's a point I'd like to make a little further. It isn't hard for someone who doesn't know very much about an area to come in a matter of a few weeks, become quite knowledgeable about the general geologic history, and then by applying IGA tools and principles, can in fact become the world expert on that area, all within a period of just a few months, maybe even just a few weeks, because it is such a powerful tool if we approach things that way. Another example comes from the Colorado Plateau in the western United States. This is the Four Corners area where Colorado, Utah, Arizona, and New Mexico come together. And this is the plateau. This is a location that I'm going to look at right now. It's a very different kind of geohistory plot, because what we can see here is it was very quiet and boring for a long time, and then the bottom fell out. Look at the tectonic subsidence curve going down rapidly in the late Cretaceous and early Cenozoic. And so we need to understand this. And then we have an inversion, and it goes up. It goes up in several different stages. Here's the first stage, then there's a quiet period, then there's at least one more stage in here, and actually then there's a third stage here. So we've got 3 different stages of uplift put into our model. So this is a model which isn't about sedimentation so much, it's about uplift. How can we work that out? And one way we can get started on these problems is to use this capability to create these overlays, which are just geological ideas. They're like bookmarks or reminders of what was going on at different times. They're totally optional, but they do help us understand this is the Laramide Foreland Basin when it went down in front of the advancing Laramide thrust sheet. And then as the thrust sheet rolled over, it was inverted, uplifted into the Laramide tectonic features and into eventually the Rocky Mountains. So how do we attack this problem of understanding what was going on in this uplift event? Much of the information we get is actually not from the rocks themselves directly, because we weren't depositing a lot of things, but from other things. So for example, the presence of crocodile fossils in the Green River Shale, which was a famous lacustrine, organic-rich, fossiliferous source rock, Crocodile fossils indicate a warm climate and therefore low elevation. You see, one of the problems with the Green River Formation is it's clearly lacustrine, it's clearly early Eocene in age, around 50 million years, lasted about 7 million years, but it wasn't clear whether that lake formed down near sea level or up in the mountains after the uplift or during the uplift. And the fact that crocodiles were living here was enough to show us that this was a low elevation lake, because if it had been up higher, it would have been too cold for the crocodiles. So that's a pretty easy call, but it shows the creativity that we can bring to a problem if we want to. Another thing in this area is the heat flow. I'm not going to talk very much about geothermics in this course because it's only a very minor part of IGA, but I do want to mention that the Western United States, and our well is right about here, is hot because of all the tectonic underplating and extension and so on that has gone on here. So we need to be prepared in this for possible volcanic events or effects and anything related to high heat flow, just by keeping this in the back of our minds as we go through this. So on the Colorado Plateau, we have proposed that our first uplift event was actually the second one, was the Basin and Range thermal uplift. So we get that from what was happening out there and to the west of there. High temperatures caused by high heat flow in that area because of the extension. So we've connected to our geothermic model both for the thermal uplift and also for the emplacement of this basalt layer that's around 70 meters thick and is still preserved on many of the mesas. So we know a lot about that basalt, but we know that here it was breached, fully eroded, and completely gone today. In fact, we've eroded all the way down to the Cretaceous Mancos Formation, having removed the uppermost Cretaceous and several layers of Cenozoic strata that were once there. And we can analyze this further. Here's our basalt extrusive on a plot of erosion rate. It says sedimentation rate, but where the sedimentation rate is negative, then it is erosional. We had slow erosion when the basalt was present because it was so hard. Once the basalt was breached, we had faster erosion until we hit the heavily cemented Green River limestone, which again was a cliff-forming formation and eroded very slowly. But eventually it was breached. We moved back to high erosion rates, slowed down a little here, and then moved to very high erosion rates, not because we reached softer rocks, but we changed our erosion mechanism. Instead of just generally eroding mountains, we were now downcutting the Colorado River from about 5.5 million years to present day, removing more than a kilometer of sediment. And that is what has caused this rapid erosion here. And it's really a catastrophic thing because huge boulders, 2 meters across, are found as much as 30 kilometers from their point of origin. They know that by the mineralogy. And consequently, there was some really crazy stuff going on during the downcutting phase here. I mentioned earlier that IGA operates on different scales simultaneously, plate scale, prospect scale. Simultaneously, it also operates in a variety of scientific areas, and we want to integrate those. Basin modeling, when it becomes IGA, is not just for button pushers and not just for basin modeling specialists. It is for all kinds of geoscientists. They may not be the principal movers and shakers in a basin modeling study, but they can all make contributions. This would include, of course, geology, but also chemistry and physics, especially if they have a geo attached to them so that they're contributing in the geologic realm. But even just talking to pure physicists and pure chemists can sometimes be interesting and useful for some of the more special questions. So we want to bring in a lot of different phenomena, as many as we can. So isostasy is an important one that we would like our software to handle as easily as possible. So for example, if it's operated in a default mode, you don't even have to worry about it. We'd like to include eustatic sea level changes through having one or more options of global sea level curves, for example. And just to show you what we've got here, this was a plot in the Gulf of Mexico in which the water depth, lacking actual biostratigraphic data, this water depth was predicted based on area isostasy and the cooling subsidence of a rifted basin and so on, to give us this pattern of evolution of water depth through time, and also resulting in a tectonic subsidence curve that is controlled by the rifting process all the way to present day. And you'll notice as the basin fills in here, the tectonic subsidence curve is still going down. It's not going up. So the filling of the basin had nothing to do with tectonic uplift at this location. Instead, it had everything to do with the sediment supply. Starved basin here, not starved anymore. And here it's a basin that's getting fat very quickly as we deposit very, very rapidly in recent times. So that helps us understand the relative importance of the different physical events during the evolution of the basin. Paleobathymetry and paleoelevation information can come from many sources. For example, biostrat data that will tell us something in words like interneritic or upper bathyal. For individual samples that can be age dated both by biostrat and by interpolation. Geological analysis might help us, and that's a very general term, for different formations where we don't actually have biostrat information. The same can be said for time periods rather than rock units. We can have theoretical considerations, rifting subsidence theory, thermal versus tectonic effects, and so on. And multiple lines of evidence may help us estimate paleoelevation at specific times in the past. You remember the case of the crocodile teeth, but I have a couple of more examples I'll share with you later. Here is an example of data and data gaps. These are data, biostrat data from a well, this well that we are modeling. And you could see some of the points were highly confident picks about water depth, and others are depth ranges. So for example, this would be upper bathyal, 200 meters to 500 meters. This, in fact, says the sample was indicated as upper to middle bathyal. So it could have been anywhere as shallow as 200 meters, as deep as 1,000 meters. So we've got these data coming to us from biostratigraphy. Over here, we've got some data from the late Jurassic that have come to us from a well in a different part of the basin that we think experience the same depositional facies because it's the same type of source rock. So we use that information from another well hundreds of kilometers away to help constrain the early water depth history. But in between, we've got a gap. And here we've got the non-marine portion, so we have an anchor point here. But what we want to do is to turn this into a little mini narrative, the story about the water depth history. So how are we going to get from this point to this point, and from this point to our deepest and oldest data from our current well? Well, we have to be clever about that. And I will talk more about that a little bit later, but one of the things that I want to emphasize again is rates. I can't say it enough because it's something that for whatever reason, geologists occasionally mention, but seldom really think about or use. Rates of deposition, of course, rates of erosion, rates of uplift, tectonic subsidence, rates of thermal events. Are they getting hot or getting cool as fast or as slow as they should be? Are we being reasonable in our expectations? Pay attention to rates. Very few other people do, and that causes them to make some mistakes. So I'll just say a couple of things about rates, and then we're going to take a short break before we have the second part of tonight's lecture. And that is, you can plot sedimentation rates. In this case, sedimentation rate is always positive, and there is nothing negative because we didn't actually have any unconformity shown in this section. There was always deposition going on. What you see is early, the rates were very low, starved basin conditions. Then it began to get faster and faster. And then if our data are good, we had an event here where the increase in rates was interrupted. Something happened here if our picks of tops and ages are correct. Something happened here that changed the history. This is a warning. We need to figure that out. We can't just pretend it was business as usual going from here to here to here. It wasn't business as usual at all. And we need to understand that. So we'll look at for verification by looking at other nearby wells. We'll look at the biostrat data to see if we trust the tops. We'll talk to the seismic interpreters, et cetera, et cetera. Then we've got this little period here where the rate picks up again. Why is that? Kind of looks like maybe we generated a new sediment source for about 20 million years, or maybe 15 million years. A new sediment source, at least for this area. That's interesting. What tectonic event created that sediment source? So we now have some homework to do to figure out not just why do we have, or how do we explain this high sedimentation rate, but give us the details about it. How does that connect to other geologic events? And then why did it slow down? And then why did it apparently speed up again so much very recently? All of these are very, very important issues, or as I like to say, opportunities to learn something. One of the problems, however, is You've got to invoke quality control at every step along the way because there are bad data, there are bad interpretations, and there are also cases of bad luck. For example, this is a very short event. If we make a little error in the beginning age and the end age, we might easily change the rate here by a factor of 2. And so we shouldn't take these numbers too literally. It's probably fair to say that it was a relative maximum in sedimentation rate, but it may not have been quite as fast as this suggests. That's just a warning. It's not necessarily true in this case, but always walk around looking for things that don't fit, looking for things that are strange or might not be correct or trustworthy. That's where you're going to make your big discoveries that will enable you to learn things other people don't know. And this just shows rates of erosion. We've got several unconformities here, each one considered mildly erosional, but clearly the erosion rates are very slow compared to the later deposition rates, comparable to the early deposition rates, in fact. Okay, I think now is a good time to take a break. Let's take 10 minutes if you'd like to get a drink or use the restroom or something, and then we'll start again in 10 minutes. Thanks. Josias, can you hear me? I just wanted to talk to you a little bit about the Novva licenses. Here's what I propose. There have been several people, both for IBA and not for IBA, who have already contacted us about licenses. I'm wondering if you can take charge of informing everybody about this plan. First, the IBA people need to go through their faculty advisor as last year, where they send a list of everybody with email and everybody gets his own license. Okay? We've had some individuals who have already asked separately for it, but we're not going to send them licenses one at a time. For people who are interested in trying Novva, a demo, but are not in IBA, I would suggest that we send to UFRJ a floating license with multiple seats, and they would be available to the people in your department as a demo version. And we'd probably give it to them for about 6 weeks.
And will work fine.
That would mean we only send you one license, a floating license, and you have to make sure your IT person puts it in properly and so on.
Okay.
And then it would be available to anybody within the department during that time period.
Perfect. You can hear me now?
And yes, I can hear you. And
okay.
I'll leave it to you. I'll leave it to you to explain that to the people in your department, those two programs, one for IBA that'll be done as a group, and one for everybody else who will get a demo, access to the demo version through the license on the server rather than on their individual laptops.
Perfect. So just to make sure if I get this right, the IBA people will ask the license as we did this year by our faculty advisor. So let's say Leonardo Borg will have to write an email with the people listed, and then we made a formal request to the IBA license. And the people that are not on the competition should try this float license that you will give to our university, a float license that our IT must install on some server or computed, and then they will try to, they can try the software as a demo. So did I get this right?
Right. Anybody who has access to that server could use the Novva demo license during that period.
Okay, that's perfect.
So it should either be a department server or a university server.
Yep. That's actually very good. So I will chat with our advisor and try to make this work out.
Right. Yeah. Just to advise everybody in the department. I won't make a general announcement. I'll leave that for you. Okay. I think
Thank you
it's
again,
time for
Douglas.
us to get going again.
Perfect.
So let's
Go on.
see. I'll try to share. Okay, I think it's working. Hello, I hope you're back. I'm going to start the second part of this lecture with a very brief discussion of paleolatitude, which you probably don't really even think about very much. but it's actually potentially quite interesting and important. And I just put this in as an example of creative thinking that can be valuable when you're working in the IGA mode. Frankly, there is no set pattern for how you use IGA. IGA is a toolbox, and you can use it however you want. Most people would not think that paleolatitude was very important or interesting. Some would recognize it will affect surface temperature, but that's all they would think about. So here is a paleolatitude reconstructed for a location in the central Gulf of Mexico through time for the last 250 million years. And you could see that it moved northward for quite a long time, and then for quite a long time, over 100 million years, it's been at more or less the same latitude. Okay, that's interesting. But if we look at the Delaware Basin, which isn't too far away, it's part of the Permian Basin in West Texas, and we look at a longer time scale, and we annotate it with different important tectonic events, you can see that what was happening here was South America was beginning to contact. Some of the outlying islands were beginning to contact the Laurentian plate, Laurentia, the old North America plate, quite early. And then we had what is called the Ouachita orogeny, Ouachita wrenching, Ouachita thrusting, start of Triassic rifting as Pangaea began to fall apart, formation of the North Atlantic, and then the West Coast severe and Laramide events. But what I find very interesting about this, and most people probably wouldn't even think about it, I didn't at first, but you've all seen animations of North America coming together with Northwest Africa, South America, Northern Europe, and so on. And it tends to be shown as North America in the West is hitting Europe and Northern Africa on the east. So you think it's moving west to east. And in one sense, it is. You can see that during this period, the movement was right at the equator. So it was moving pretty much west to east. But before that, it had been moving south to north fairly fast. And so this east to west movement was perhaps not its preferred direction of movement. It was simply caused by running into other tectonic blocks coming from the east. Once the rifting started and Pangaea started falling apart, I'll bet you were thinking North America went back to the west. It came from the west, it bounced off and went back to the west. In fact, that is not what happened at all. It headed north again. So it was very, very determined to move from south to north, and it took the collision with Europe and South America and Africa to slow it down. But once it was given an opportunity, it continued north again. I had never thought about that, never realized it, but it shows that useful information and useful ideas can come from many sources, often unexpected sources. Global climate is something we want to take into consideration because there has been so much variation in global climate. And without talking about modern day global warming, I want to point out that the present day is very close to the coldest that the Earth, as on an average, has been for at least 500 million years. So it really has almost no place to go except to get warmer. And this cooling has been in effect for about 200 million years, or perhaps only 100 if you want to start it there. Sorry. But the differences are large. They're 10 degrees, 15 degrees, even 20 degrees Celsius in surface temperature, maybe even more in some rare cases. So global climate is something we should think about. But another interesting thing about global climate that you may or may not know is that it doesn't affect all latitudes equally. The black line here is the modern world. And what we see is that at the equator, latitude 0, the temperature difference between a hot world and a cold world is, well, it's there, but it's not extreme. Whereas as we move toward the poles, those differences can become very, very large. And consequently, we've got to really understand not just global climate trends, but also paleolatitude, which is going to go together with global climate to control our surface temperature. And our surface temperature is important. It will affect erosion. It will affect downhole temperatures, geothermics. So this is potentially an important and interesting part of the story. I guess I should say that what I'm trying to do tonight and in 2 days is to give you a sampling of all the different questions and problems you can address and even recognize with IGA. I'm not trying to teach you how to do any of these specific things, at least up to now. I'm trying to raise your awareness. That is all. But once your awareness is raised, you should be able to do this yourself quite easily, getting better and better with practice. I want to look here in some detail at a location in central Algeria. I want to look at the geologic history. Here it's presented as a typical strat column in which the unconformities, and there are many of them, are shown in red. And then we've got our depositional strata with ages here. So this is a typical column, strat column that you might find in a published article, for example. Now what we've done here is added some dates to this. And so we see down here the Cambrian, the post-Cambrian unconformity lasted for 20 million years because end of Cambrian, let's say the age preserved at the top of the unit was 500 million years. The age at the base of the newly sedimented middle Ordovician is 480. And we're missing the lower Ordovician or early Ordovician. We have a 20 million year time gap, and we have time gaps long, short, at all of these locations. This is our biggest time gap, 360 to 144. Here's our second biggest, 130 to present day, because we have Neocomian age rocks at the surface. So this is, again, a pretty typical strat column with a lot of information in it. That information would look very much like this if you plotted it, where we have some periods of sedimentation, but we have a lot of erosional periods or unconformities. And in fact, it is not uncommon, as we have here, for the periods of non-deposition to be longer in total than the periods of deposition. We don't think of it that way because we can see rocks, but we can't see missing rocks. But it is really true. So that's an important thing to take away, that If you're going to build accurate models, they're going to be like Swiss cheese with a lot of holes in them, a lot of places where we have unconformities. And for most people, that makes them very unhappy. Because if you don't have unconformities, you can just ask the geophysicists or the geologists or the micropaleontologists to give you a bunch of tops, and you just put them on top of each other, and your job is done. You got continuous stratigraphy, few unconformities, no big problems. Okay, that's fine when it happens. But if nature gives you unconformities, I strongly recommend that you think of them as opportunities rather than problems, because every unconformity is an opportunity to learn something new and understand something better. Because unconformities are unpopular. People don't like to do the hard research work, the digging, sometimes literally, and the thinking to figure out what actually happened in unconformities. So they take the easy way out. They call them hiatuses, or they just throw in some numbers and forget about it. They just want the unconformities to go away. That is unfortunate. It's sad, because the people miss out on the most interesting and fun part of doing these reconstructions, which is figuring out what happened during unconformities and linking it to the stratigraphic history, the lithologic history, to the tectonics, all the other pieces of the puzzle to create a good narrative. So if you want to be lazy, unconformities give you a chance to be lazy. But if you want to do that, you will never be any good at working with IGA. To work well with IGA, you have to love unconformities and see them as opportunities to learn and to become literally the world expert on that unconformity. So we're going to learn how to do this. And I'm going to take one example here and work through a very simple unconformity here in some detail to show you the type of thinking that can go into this and how it can be interesting and fun. We're going to look at this 20 million year unconformity where probably part of the Cambrian is missing. Certainly the whole early Ordovician time period is not represented. And we may also be missing the lower part of the middle Ordovician. We don't know. We're going to have to make some assumptions. Okay, so we're going to look at this 20 million years of missing time. Was there erosion? Probably, because 20 million years at the surface will almost always cause at least some erosion. If there was erosion, and this is one of the most important messages I'll give you today, the missing rock must have been deposited before it was eroded. We all know that, but we all forget it. We start thinking about erosion. Don't think about erosion until you think about deposition of the missing rock. So there are pairs, deposition, erosion pairs for every layer that has been eroded. And you're going to have to specify that. You're going to have to specify how much and when. And you should do it logically so that the numbers and concepts fit together and you're happy with them. And why do you do that? 2 reasons. You want to build the best model possible. And if you do something stupid, or lazy, somebody is going to notice it and ask you a question about it during an important presentation. So for self-preservation, do good, complete work. All right, we're going to assume that the deposition of the missing rock began at 500 million years. When did it end? All we know is sometime between 500 and 480 when the new sedimentation started. How can we estimate when the deposition ended? Okay, now we have to make some assumptions. But a very logical assumption is always that erosion does not go down to the depositional top of a unit and stop there. That could happen when you have some very, very hard rocks, like a basalt with sands and shales. But more likely, there's going to be something missing. And in this case, it would be the Cambrian. So it would be logical to imagine that the Cambrian has some erosion off the top. And that means that we have to deposit some Cambrian, and then we have to decide what to do about the early Ordovician. Are we going to deposit it or not? So we've got some decisions to make about what to do, and how are we going to make those? We're going to think hard about it, research it, and also look at nearby locations. So let's look at the rates. The rate of deposition of the preserved Cambrian, which is 150 meters thick, in 43 million years, and I want to just show you, the 43 million years came from this. That's 3.5 meters per million years. So immediately you understand this was very slow sedimentation. Time available for deposition of the missing Cambrian, if we assumed, and I think I said that somewhere, I assume that the Cambrian ended at 490, and so if we deposited the entire Cambrian, it could have been 10 million years. So we might have had as much as 10 million years. If we deposited the entire Cambrian, 10 million years missing, the rate is 3.5, so we're missing 35 meters. If for some reason we think we know there's 100 meters of total erosion, that means the early Ordovician had to deposit and erode 65 meters. The maximum time available for the early Ordovician would be 10 million years if you took it all the way to the end of the early Ordovician. But you have to actually use some time for erosion. So you have to partition or separate this time period into period for deposition, period for erosion. And in these next two, I just said if you had short deposition, then your rate of deposition to get 65 meters is going to be too high. And if you have very much time for deposition, but very little time for erosion, your erosion rate would have to be too high. So we have to find a compromise here. And so we go back to our data. The early Ordovician was deposited at 13 meters per million years. So it was pretty slow. And the erosion was at a rate of about 20 meters per million years. If we like that, after assuming that we had 5 million years of early Ordovician deposition and 5 million years of erosion, then we're finished. And we've done it logically. People may not like our model, but we have done things according to good scientific principles. That's all we can ask at these unconformities. And I like to speak of events rather than rock layers. For me, the pile of rocks is lifeless. It's just sitting there. I'm interested in the process that created it, to make it a dynamic story, like history, in fact. And so I call these events. So I like to talk about deposition of the Upper Cambrian or deposition of the early Ordovician or erosion of one of those units rather than just talking about the rock layer itself. That's just my personal preference, but it may be useful for you also. So if we look at it in terms of events, I have 4 events pictured here. Deposition of the Cambrian, deposition of the early Ordovician, erosion of those 2, and deposition of the middle Ordovician. The period here, 543 to 490, 185 meters deposited, which is 150 meters that was deposited and remains, plus 35 meters that was deposited and eroded. So now we deposit this, we erode the total, and then we go back to depositing this. And when we look at our rates, we see that everything is pretty slow and pretty consistent. And so we ought to be feeling pretty good about this because we haven't done anything crazy. We haven't changed things very much. It was more or less business as usual right before this unconformity and right after it. Those are principles that I use in working through examples like this. I look carefully at rates. I look carefully at amounts. I look carefully at what is preserved and what would be a nice, safe, reasonable proposal. One thing you have to remember when you're reconstructing unconformities is that time must be continuous. There has to be something occurring, some event at every moment. No time gaps are permitted. You can have time gaps in your stratigraphy, but you cannot have time gaps in your story. Now, not every unconformity is pretty simple, like the Cambrian unconformity there. The Hercynian in Algeria has a time gap of 200 million years, with several kilometers of erosion, with some deposition, and reconstructing this is a lot more complex. Here we're going to do it by comparison as much as possible with preserved sections nearby. Fortunately, erosion did not go to the same level everywhere. So we have some very young rocks, partly preserved, that help us understand the rocks that are missing. So here's a geohistory plot of a location in central Algeria. You add the downwarping here is in a foreland basin in front of the advancing thrust from the Hercynian orogeny that brought Morocco and Algeria together with northeastern Laurentia in America. Deposited all these rocks, and then we eroded all this green stuff here. We built some mountains, eroded that off, maybe eroded off a little bit of the Strunian here, and then later we deposited some Cretaceous. Okay, but we're interested in this event here. We need to reconstruct the amount and type of rock that was deposited here. And that is done, as I said, by analogy. So we've got all these events here. The green one is a hiatus, sorry. Black ones are deposition, and the red is erosion. Whole series of events reconstructed here in a logical way that agrees with the preserved sections as close to this location as possible. Now, as another example, we have the Permian Basin. The Midland Basin is part of the Permian Basin. I want to look at the huge unconformity between the Cretaceous and the Tertiary. And what has happened here is that we had many different Cretaceous units that are well defined and well preserved at other locations. There's about 11 different units in this reconstruction, most of which were completely eroded. But they were reconstructed here, and then they were removed in 2 successive erosions that were caused by 2 different tectonic events. And so we not only had to partition the deposition among 11 different units, but we had to partition the erosion between these 2 very different events. This one in our reconstruction being slow, and this one as being fast. This reconstruction was something I worked on about 7, 8 years ago, and I hired a man who was said to be the world's best figure on authority expert on the Cretaceous of West Texas. I hired him to do the reconstruction for me, but I told him how I wanted him to do it. I said, you can divide this up into as many units as you want. And he chose 11 of these with 5 different unconformities between various layers. It was very detailed, very thorough, very nicely done, based on his knowledge of 5 different sections that surrounded this area and gave you a window on what was once present. And I said, you have to do it as a series of events, putting it back together, thinking first layer, second layer, third layer, what was deposited, where was it deposited. So he had to create a whole series of maps that showed the reconstructed thickness across the entire area. Put it all together. It was a very nice piece of work. And at the end, I congratulated him. This was a man who had spent 50 years working on the Cretaceous of West Texas. And he said, oh, it was a real pleasure working on this with you. He said, I learned so much. And I thought, wow, that is a powerful statement to take a person who's the world expert and is dedicated to career to that. And by simply looking at the problem in a new, creative way, he found things he could learn. I think that's the best testimonial you could have for a technique like IGA, that it is telling people new things, giving them new insights, and we all know what that's going to lead to. That's going to lead to new exploration ideas. Which is the best model? Well, there is no general answer to this. It depends on your concepts and the concepts you believe in and are willing to defend. Every number, amount eroded, rates, even lithologies that you put into a model has physical meaning and implications for what was happening. These numbers should represent your best concept of what actually happened. So stop asking yourself how much erosion as your first question. Start asking yourself, what happened here? What were the events that I am trying to reconstruct? You may be asked to defend any particular number or concept in your simulation, so be prepared. And the best way is to do good, thorough background work. Choosing the best model is not easy. It is not for lazy people. It requires deep thinking and strong efforts to find and to integrate data from many sources. Remember, data don't come walking into your office. You have to go find them. And data are not all perfect. Quality control must be used to separate the bad ideas from the good ones. But in the end, it is worth the effort because you learn so much about the geologic history that will be valuable whether you're looking for oil or gas or uranium or lithium or whatever it is that you're exploring for or that you want to learn about. Because the right solution to any problem of work is get the right tools. And IGA is the most powerful and effective tool available. I want to go back to the slide I showed you earlier with all the foreland basins here related to the laramide orogeny. This is the Colorado Plateau that we looked at with the basalt layer. You can see it's part of that system. We didn't really talk about it then, but everything that we learn in this basin is going to be applicable in some way to these other basins. And conversely, everything from these other basins can be brought back to this basin. We have the Powder River Basin. We also have the Anadarko Basin and the Permian Basin. Now, the Anadarko Basin and the Permian Basin are not directly in the laramide environment, but they are affected by it. And there are events related to or that occur in the Permian Basin and the Anadarko Basin that are very parallel to similar events in these basins. So understanding these basins, even though they're directly laramide basins, is helpful in understanding these other basins as well. In particular, if you can find maps like this is a paleogeographic reconstruction. Ron Blakey has his own website, which you can find, and a lot of this stuff is now for sale. It used to be free, but these beautiful maps of much of the world, and in particular North America, Western Interior Seaway in the mid-Aptian at 115 million years, not yet very well developed. It was mainly developed around 100 million years ago. Here's the Permian Basin roughly. You can see that it was beginning to come down to the Permian Basin. There's also encroachment from the south into the Permian Basin, and this seaway became a throughway passage in the mid-Cretaceous. And here it is later at the end of the Cretaceous at 65 million years. It's dried up, but it dried up by retreating to the north, retreating to the south. And again, we don't see anything in the Permian Basin. But during the time between these two, this whole area was underwater. And that's the rock that is missing today that we just reconstructed. Go back to the Colorado Plateau. I mentioned the crocodile fossils here. I want to talk a little bit more about it and the Anadarko Basin. You see, the Colorado Plateau, as I said, is part, sorry, I don't have the slide here. Part of that system, the laramide system. And these two basins here is the Colorado Plateau right over here, are a bit further away, but they're still relevant to this. The Permian Basin is here, the Anadarko Basin is here. Now, if we go back up here, they look rather far apart. But what was happening was all along the suture here, there was a collision with Africa, Northwest Africa, Morocco, and so on, and South America in here, several different collisions hitting at different times. These are part of the collisional system. You see that here. Here's the Ouachita. These are basins on the east side of the Ouachitas, and these are basins on the west side that wound up as part of the United States. These wound up as part of Mexico or other places. And what you see is these are two different places in the Ouachita collision. They are both part of the same system, but they're not coeval. The Anadarko Basin is about 30 million years older than the Permian Basin, and the direction of stresses and types of stresses are not exactly the same. You can see up here how everything came together, and these locations are right in this area here. So they're analogs, they are cousins, but they're not super close cousins. And so you have to be careful about how you use one to help you understand the other. There will be false analogies as well as true analogies. Here's the Permian Basin. Actually, let me start with the Anadarko Basin because it's older. They got out of order. What we see here from the colors, we got Permian strata deposited near the end of this event, but we've got Carboniferous strata deposited earlier. So if we want to call the Permian Basin because it's mainly Permian, that's fine. We should probably call this the Carboniferous Basin then, because it bridged the gap between Carboniferous and Permian. We can tell that quickly from the colors. That's a very nice thing. We also could see that there was rapid and large tectonic subsidence. We can also see that we have basins that are very deep. This is almost 9 kilometers at this location, but only about 4 kilometers is tectonic subsidence. So how did it get to be 9 kilometers deep? Because of loading subsidence. So the total subsidence shown by the black line is much greater than the tectonic subsidence. We don't need such a huge force to give us a very deep basin. Once we get started with 1,000 meters of tectonic subsidence or 2,000 meters, we have a very good hole to start putting our sediment into and making it significantly deeper. Now, if we go up to the Permian Basin, we see a similar pattern going down over a significant amount of time. It's almost as deep. It had a bit less tectonic subsidence during this phase, so it's not quite as dramatic. Very little happening in the Carboniferous. Definitely a much later event here. But one thing that they have in common is Triassic and Cretaceous. You see, at this location in the Delaware Basin, we had Triassic deposited on top of the Permian, followed by Cretaceous. Here, we had no Triassic in the Anadarko Basin, and our Cretaceous is thinner. We had Cretaceous at both, but it's not identical. That's very interesting because the subsidence event that gave us the space to put the Cretaceous affected both basins, but again, they're not identical. So we have good analogies, but not perfect analogies, and our narrative will emphasize the similarities when they are appropriate and it will emphasize the differences when the differences are appropriate. In contrast, when we get to a different basin, we see something totally different. In this case, it's the Powder River Basin, a northern laramide basin. And what we see is here we had almost no sedimentation for many hundreds of millions of years. This is given rise to the Wheeler sequences, the first real effort in sequence stratigraphy, where Harry Wheeler, more than 60 years ago, broke up North America into all these sequences: Sauk, Tippecanoe, Kaskaskia, Absarica, Zuni, and so on. That's what we're seeing here. So it's a study in sequence stratigraphy, not in tectonics, for this part of the story. And those are the overlays we put on to enable us to discuss them. And then the severe foreland and laramide foreland developed between these two events related to the subduction of the Farallon plate. And so things started going down. We have tectonic subsidence here, and that is accounted for by these tectonic events, the advancing thrust sheets, and we see the results. We created a pretty thick Cretaceous section where prior to that, sedimentation rates were very, very low. So it's a huge change heralded by the laramide event. And then that's not the end of the story. We deposited a very thick non-marine section here, and then we uplifted it and started eroding things. So starting about 100 million years ago, this very, very boring place suddenly turned into Las Vegas, and all the action started happening here. I think since we've used up our 2 hours, I'm going to stop here for today, and we'll continue with this, and we'll have a look at Novva also 2 days from now when we do the second session. And I think that Josias is going to make an announcement for you regarding access to Novva for both the IBA people and anyone else from your department or anywhere else who's interested in getting a demo copy of Novva to play with themselves. So with that, I'll say thank you and good night.
Well, thank you, Douglas. Excellent presentation. Well, I have one question here for you, if you have a few minutes to answer.
Yeah, I have time.
Okay, one thing that got me curious, first, great presentation so far. We got a lot of comments on our WhatsApp group. So one thing that intrigues me is, well, you are the mind behind all the integrated geological work. Your speech today was about that. But how was this transition from the idea and the software? So you have a group of software engineers and geologists with technological affinity, or you got this thing right on paper and demand to some company. How was this thing made?
How was Novva made specifically?
Yes.
No, okay. I had been doing modeling. I was one of the very first people to get into this modeling just through luck in 1974. So that's 47 years ago. And I've been working in it since then, not every day, but I've done a lot of modeling. And I knew what I liked and what I didn't like in software. And I knew what I liked and didn't like in technical capabilities for software. So the UI of the software was important, but also the technical capabilities and the whole philosophy of giving people options and choices, giving them a lot of help, not assuming they're specialists or they're going to be using it all the time. And I finally got tired of using other people's software that wasn't doing things the way I thought they should do it. And I just said, how much savings do I have? And I thought I maybe had enough to build some software. And I was wrong. Of course, I grossly underestimated the time and cost, but I hired a guy fresh out of university who was brilliant and did a great job. He knew absolutely nothing about geology, but he had a good foundation, not only in computer science, but also in math and physics. And so he understood how to work with math and equations and solve problems and so on. In other words, it wasn't a guy who built business software, he built scientific software.
Mm-hmm.
But it was his first job. I mean, he was 22 years old, and I hired him, and he did a brilliant job of taking my ideas and translating them into usable software. Virtually every idea in the software, from the user interface to the technology, is mine, but all of the coding is his. And we work together as a team because we each had different skills. We each had different tools in our toolbox. So we built it. It took about 2.5 or 3 years to get it to where we could release it and where I could use it for consultancy work. And fortunately, I'd done enough consulting at that point and done enough modeling that I didn't make too many mistakes in the content or the design of the software. We've added a few features as time and money permitted, but basically it looks 95% like it did 10 years ago. Well, almost 10 years ago, 8 years ago when it was first released.
Mm-hmm.
So I'm happy about that I was able to anticipate in advance most of the features and capabilities that I would want. And handle the other ones in some way. So that's the story of it. It was built out of my need to feel more technically comfortable with the software available and not having anything I could buy.
Perfect. Oh, great story. So you got a youngling from the university and combine with your ideas, and then you get this soup, the excellent soup that is your Novva software. So great to hear.
And the interesting thing is we as personalities and people, we are as different as night and day, but we found a common ground to work together. And that was the secret. He wasn't automatically an easy person to work with, and he didn't have a reputation as an easy person to work with. But we were able to meet halfway, and I think he did a wonderful job of putting it together, and I feel happy that it has the technology that I wanted in it.
Yes, it is very interactive. The Novva software, people may use it on the upcoming course on Thursday. So you guys can see it. It's very interactive. It's like an interview that you made and got a lot of patterns. Douglas and I don't know what the name of this young lady is, but they made a great job on giving all the the answers that we need to build our modeling as easy as it can get and a reliable model. So I guess we don't have any more questions for today. So thank you again, Douglas, and see you on Thursday. I will make an announcement
Okay.
later by writing for our people. And well, guess I'll see you on Thursday. Thank you again.
Will you be sending another link to log into? It's not the
Yes,
same one,
yes.
right?
We are going to send you another link, a new one.
A new one. Okay, very good. Thank you. Thanks to all of you for bearing with me for 2 hours, and I hope the coming 2 hours will also be useful for you.
Thank you again, Douglas. Só para terminar
Okay,
então, pessoal,
thank
I will
you.
speak in Portuguese now, Douglas, to make the announcement, okay? can I speak in Portuguese to make the
Oh, it's
announcement?
fine. You don't
Okay.
need me anymore, right?
No, you can.
Okay.
You are free to go. Good
Goodbye.
night.
Goodbye.
Bye, bye. Então, pessoal, em relação, aí mais orientado a galera da APG, né? Em relação ao software, o pessoal que a gente vai lançar as inscrições para nossa equipe IBA, e ela deve rolar até sexta-feira. Então a gente não vai ter a nossa equipe definida, que era o nosso intuito, né, até a próxima aula do curso, que aí a gente já conseguiria essas 5 licenças definitivas, e vocês poderiam ir usando até que quando chegasse a competição, vocês já estariam craques. Então a maneira que a gente vai encontrar é o seguinte, a gente vai passar aquela listagem de novo, das 5 pessoas, e essas 5 pessoas a gente vai incluir no e-mail que o Borg vai mandar para o próprio Douglas, e vamos tentar agilizar o mais rápido possível para que na quinta-feira vocês já tenham o software em si. De qualquer maneira, esse curso ele vai estar gravado, então vocês vão poder ir explorando com o tempo também. Mas uma outra parada que a gente conseguiu, que o Douglas acabou de anunciar, é que a gente vai ter uma licença no estilo Float, ele vai instalar isso no servidor, vou estar conversando aí com o Eduardo, com o Borg, se isso é possível lá no servidor do Laje7, para que qualquer um que tenha um e-mail institucional consiga acessar essa demo e explorar algumas features do software, beleza? Espero que vocês tenham curtido o curso e vejo vocês na quinta-feira. Valeu? Então é isso. Tchau, tchau.